In this video, we would like to do some sample calculations involving a weak acid. As we recall, we take a generic monoprotic acid, which we often represent as HA. If it is a weak acid, then it only partially dissociates in aqueous solution, so that we get H+, which we often call a proton, plus the conjugate base A-. So this is a convenient way of representing just some generic weak acid. For this particular video, we want to look at a specific weak acid, hydrazoic acid, which has the chemical formula HN₃. And we've picked this particular acid because it is very common to do calculations with acetic acid and hydrofluoric acid, so we figured we'd at least do something a little different. So, in aqueous solution, it dissociates partially to form H+, and also the azide N3-1 ion. As we recall, for any chemical reaction, we can write an equilibrium constant. And in this case, the equilibrium constant is going to be the concentration of H+ times the concentration of azide ion we recall that anything that is a product, anything that is on the right side of the reaction, is going to be in the numerator of the equilibrium constant, and any of the reactants that are on the left-hand side will be in the denominator of the equilibrium constant, though there are some exceptions to that. So this is the overall equilibrium constant for the dissociation of hydrazoic acid in aqueous solution. This particular equilibrium constant occurs so frequently that it gets its own special name and special symbol, so we call it the acid dissociation constant, and we give our K a small a subscript. Let us rewrite our equilibrium constant one more time on a fresh board. And we have our proton on top times the concentration of azide ion. And one thing that is good to review at this point is that even though the products are linked together in the chemical reaction by plus signs, we multiply the concentrations when we calculate the equilibrium constant. And the denominator, of course, is the undissociated HN₃ hydrazoic acid. If we consult with a reference work, we would see that the actual numerical value for this equilibrium constant is 1.9 times 10 to the minus 5. So that's a specific value. What we want to ultimately do with many of our weak acid calculations is, starting with a known concentration of the acid, determine what the pH is going to be. So a common way of representing the initial concentration is to use a small c and then a subscript HA, just to refer it to a generic weak acid. Or if you want to be more specific, in this particular case, we know that our weak acid is hydrazoic acid, so we might even write HN₃, and a typical concentration, and the concentration that we will use for this particular example will be a concentration of 0.1 molar. So we want to determine the pH. As a matter of efficiency, it is usually easiest to first do an intermediate calculation where we calculate the concentration of H+, and then, knowing that particular value, proceed in a second step to determine the pH. So let's show how you would determine the H plus concentration for a 0.1 molar solution of hydrazoic acid. What we're going to do is we're going to set the concentration of H plus equal to the variable X. One thing which we also notice is if we rewrite the reaction that hydrazoic acid undergoes as it dissociates, or you can just back up in the video, we notice that for every 1 mole of hydrazoic acid that dissociates, we get exactly 1 mole of H plus and 1 mole of azide ion. The H plus and the azide ions always come in pairs because we're starting with a undissociated complete molecule of hydrazoic acid. I'm going to emphasize that point because when we deal with certain salts, this will not be true. But if we're starting with a weak acid, the concentration of H plus will be exactly equal to the concentration of the conjugate base. So at the same time as we set X equal to the concentration of H plus, we can also set it equal to the concentration of azide ion. Now we can substitute these values into the expression for the acid dissociation constant Ka. So H plus has a value of X. The concentration of azide ion has a concentration of X. Then we get to a slightly tricky part. In the denominator, this concentration HN₃ is the concentration of the hydrazoic acid that has not dissociated. So this number will not be exactly 0.1 because though we started with a formal concentration of 0.1 molar, some of that hydrazoic acid is going to dissociate because it's an acid. So the overall concentration here is going to be equal to the initial concentration 0.1 minus the small amount of hydrazoic acid that dissociates. And we realize that for every X molecules of hydrazoic acid that dissociate, we will get X moles of H plus ions and X moles of azide ions. So this particular value here is going to be equal to 0.1 minus X. And then we can set this numerically equal to 1.9 times 10 to the minus 5, and that is a value that we determined from looking up in the literature. At this point, we can solve for X. Unfortunately, it would involve a certain amount of manipulation. We can convert it into a relatively easily solvable quadratic equation, but we have two reasons why we might not want to do it. The first reason is that given our experimental accuracy, if X really is small, relative to 0.1, then it doesn't make much sense with an experimental error to really worry about reducing 0.1 by X. That's one reason. The second reason is sometimes it's just a pain to solve the quadratic, and a difference in accuracy of the answers between solving a quadratic and not solving a quadratic is not really worth the extra added effort. So let's employ a very commonly used trick or technique. And that technique is to assume that this value X is actually very small. And it makes sense because we have a weak acid with a small dissociation constant. So the total number of molecules of azide ion that dissociate is not going to be that large. So since we are going to assume that X is very, very small compared to 0.1, if X is very, very small compared to 0.1, we can essentially approximate 0.1 minus X as just 0.1. We can often do the same trick whenever we're adding a small number to a big number or we're subtracting a small number from a big number. Warning, never try this technique if you are multiplying by a small number or dividing by a small number. In those cases, this is not a legitimate technique. So, we shall proceed to solve our problem here using this particular approximation. If we make use of the fact that x times x is simply x squared, we can write the numerator as x squared. And if we make use of our technique, aka trick, that we can ignore a small value that's added to a larger number, we can write the denominator simply as 0.1, and that this is set equal to 1.9 times 10 to the minus 5. To solve this equation, we want to multiply both sides by 0.1, and that gives us that x squared is equal to 1.9 times 10 to the minus 6. To solve for x, which we recall is the hydrogen ion concentration, we need to take the square root of each side. And we're going to make use of the very important notion that the square root of x squared is equal to x. It can be plus or minus x, but in physical problems such as concentrations, the concentration will always be non-negative. Whenever we solve, for example, the quadratic also, we would always ignore any negative values for x. So just keeping ourselves to the positive values of x. And now I can find the square root of 1.9 times 10 to the minus 6. If you have a relatively modern calculator, you can simply type this value in, take its square root. But let me show you a technique which is old school, which will help you if you have an extremely primitive calculator, or if, heaven forbid, you would have to solve a problem without having a calculator at all. So here's what we do. We can make use of the fact that the square root of a product is equal to the product of the square roots. That means that I can rewrite this particular square root expression as the square root of 1.9 times the square root of 10 to the minus 6. And in fact, be careful that this is x as a variable and this is a multiplication. Now, using my calculator, I would find that the square root of 1 to the minus 9 is 1.378. To find the square root of 10 to the minus 6, we can do by inspection, because we have a even number exponent, and using the properties of exponents, the square root of 10 to the minus 6 is simply 10 to the minus 3. I take the exponent and I divide by 2. So I'm able to determine that the concentration of hydrogen ion in solution is going to be 1.378 times 10 to the minus 3. With the calculation of the hydrogen ion concentration, we are halfway to our final goal of determining the pH of the solution. Now we would like to use the definition of the pH, that the pH is the negative log of the hydrogen ion concentration. So in this particular example, we have the negative log of the quantity 1.378 times 10 to the minus 3. Again, if you have a sophisticated calculator and you're comfortable using it, you can simply enter this value, take the negative log of that, and it will spit out your pH. Again, suppose that you have an old school calculator, or the way I had to used to do it when I was in high school, you have to calculate logarithms by using tables. So how would we do that? Well, we want to make use of a very, very, very important identity for logs. So let me just put this in the corner here. One to keep in mind that comes up a great deal. And this particular fact is that the log of A times B, so I take the log of a product, is equal to the log of A plus the log of B. Not only is this a true statement, an important property of logarithms, this is one of the reasons why logarithms were invented in the first place. Several centuries ago, multiplication of very large numbers was extremely difficult because there were not mechanical or electronic devices to do that. So if you could convert a complicated multiplication into a much less complicated addition, that had tremendous practical value. So if we apply this particular identity to our problem, we can break this logarithm up into two parts. So I have minus the log, first, of 1.378, and then we have addition, but I have to carry across the minus 1 and distribute it across. So we have minus the log of 10 to the minus 3. Again, we can make use of the fact that some quantities we should be able to determine simply by inspection. We may not need to do that during the course or during an examination, but it's extremely useful because it allows us a quick double check to make sure that we've gotten a reasonable answer. So the logarithm of 10 to the minus 3, the log of 10 to the minus 3 is simply minus 3. We can think of logarithms as being almost interchangeable with the term exponent, so long as we have base 10. And minus a minus 3 gives us a value of 3. So the minus log 10 to the minus 3 part, we don't need a calculator for. We can write that down by inspection. The minus log of 1.378, that you probably won't be able to do in your head. I can't do that. So we would use our calculator for that particular expression, and we would find that this is 0.139937. Now you'll notice that even though we started with a concentration that was only known to one significant figure, and we started with an acid dissociation constant Ka that was only known to two significant figures, throughout our calculation we've carried extra digits. Not only is that legitimate practice, it's a very good idea. If you begin to throw away digits before you finish your calculation, it is very easy to truncate your answer so far that you get a gross error at the end. It's best to carry a few extra digits to the very end, and at that point, when you come up with your final answer, to adjust it to the correct number of significant figures. So now we have pH is equal to minus 0.13937 plus 3. So we end up getting a final result that the pH is 2.86. And again, we've carried a couple extra digits here, but just to demonstrate the method. We would notice also that this value is reasonable. And we want to always check it with, for our comparison, so I'll use CF, which is a Latin phrase for compare, to what would be the pH of a solution that was 0.1 molar, but it was a strong acid. Well, again, this is one of those problems that we can do in our head and we should get used to it, because we can always write a concentration of 0.1 molar as 10 to the minus 1 molar. Since it's 10 to the minus 1 molar, if we use our definition of pH as minus log of H plus, this tells us immediately that such a solution would have a pH of 1. So we notice that the pH is slightly higher than that, that tells us that we actually have a reasonable value, because a weak acid at the same concentration will be less acidic, will make fewer protons, so therefore it will have a higher pH. It is always a good idea to do this kind of calculation, if you have time, as a reasonableness check on the value that you determine doing a weak acid calculation. Thank you for your attention. Have a good one.